All right. So let me just start with another conceptual bit of information here from one of the chapters in this book, The Hands-on Machine Learning. So let's talk about the types of machine learning systems. All right. And so a few different concepts here. So, so the point of machine learning is this is the sense in which there is some intelligence. Instead of a human programmer having to write all the logic, it's going to learn from examples. And so the example I mentioned before with a spam filter, it'll learn from just a bunch of examples of spam emails and regular emails. The machine will find some patterns there without a human having to find them. And that's the training set is the list of emails, and the machine learning system that makes predictions is called a model. So the point is, in traditional programming, if you wanted to create a spam filter, you would have to find keywords like for you, credit card, and so on. And then you'd write some kind of algorithm to detect the patterns and flag how many of those patterns are detected. So this is the way normal coding works. You study the problem, you write rules, you evaluate it, you analyze errors, and you go around this loop some number of times until it's good enough, and then you launch it. And a human has to add all the intelligence. All the machine does is follow the rules written by a human. But in machine learning, you study the problem, you prepare a machine learning model, and then you give it a bunch of examples. It chooses its own rules, and then you evaluate it and see how good it is, analyze the errors, and you may have to do more training or adjust your model until it works well enough, and then you launch it. The only difference is a human did not write the rules. The machine deduced its own rules. So, therefore, one good thing about machine learning models is you can more easily update to new tactics. If you just feed in new data, you can train it again, and it can continue to learn to adapt to the changing circumstances. So, things like speech recognition can be trained on a bunch of recordings of people. All right. And so you can also have systems that try to help humans learn. This is a goal of like the educational machine learning, that somehow these will help people. And I've heard people that teach technical classes say, I now tell every student, open ChatGPT on every workstation, and every time you have a question, type it into ChatGPT, and you'll often get a better answer than your teacher would give you, like a page of a textbook customized to you. And that seems like one of the many ways to use it. So it's good for a lot of problems, as we know. And here's some applications. Analyzing images to automatically classify products on a production line. And this might use neural networks or transformers, which we'll talk about. Detecting tumors, classifying news articles. They call this sentiment analysis, analyzing things to see if they are positive or negative to sort of make a score about a new product you're launching or a political campaign to see how popular it is. This is natural language processing, which uses neural networks typically to decide what the meaning of text is. Chatbots are the main ones we see, detecting credit card fraud, predicting what products your customer might want to buy, like Amazon and Netflix do. They look at what you've previously purchased and try to figure out what you might want. All right, so here's the main types: supervised, unsupervised, and ones in between, online versus batch, and instance-based versus model-based learning. So the training level of supervision is a big issue. Supervised learning, we talked about before, is where you have data that has been labeled by humans. And this is, of course, the easiest to use, but it means you have to pay these humans somehow to do that labeling for you, and that gets expensive. Here's one supervised learning task: classification, sorting things into categories, and then regression. You have some kind of data on some kind of axes, and you're trying to predict values. So you're basically curve fitting, trying to find a smooth curve that goes through this data. And here you have some fundamental issues, like, do you really know that the best fit is this smooth curve going through it? Or is it possible that you should be going up and down these small variations? Are those small variations noise, or are they actual real variations in the data? And that's kind of a human judgment. And we'll talk about that as we go ahead. In unsupervised learning, you have unlabeled data. And you could cluster it into groups, or you could use masking, as we said before. Yeah, clustering into groups could help you with visualize the different categories of things, and they call this taxonomy in science. When you have a new phenomenon you're trying to understand, like, for example, mental illness, the first thing you do is just sort people into groups, give them a name. That's the first step towards science, is just dividing into categories and naming it, even if you're not yet ready to have an understanding of what causes these differences. So one big problem is dimensionality reduction. If you consider a Tesla, it's got a camera pointing out the front, and I suppose another camera pointing out the back. I don't have a Tesla. And that camera is giving you something like 4K by 4K pixels many times per second. That's an unthinkable amount of data. You couldn't possibly process all that data fast enough to make a decision. So you have to somehow focus on the important stuff and ignore the irrelevant stuff. That's dimensionality reduction. You somehow have to limit it down. And the human brain is extremely good at this. In the human brain, you have slow, weak processors that take milliseconds to do one cycle of calculation. And yet, if someone throws a baseball at your head, you will immediately detect it and within 50 or 100 milliseconds, jerk your head out of the way. So your brain is able to take all the complexity of all the information coming in your senses and quickly decide that one fact is important and focus on that and make a quick decision. And that's dimensionality reduction. We'll play with that quite a bit. So anomaly detection, we talked about before, is where you group things together and find the outliers. And you can find interesting relations. The machine will learn to do things differently than humans. One example I heard of this years ago when they started bringing out these loyalty cards is that they discovered that if you were at 7-Eleven, the best thing to sell more beer is to put the beer next to the diapers. And that's not obvious, but what happens is the only reason someone would go out at night to buy diapers from a 7-Eleven is because it's midnight, and it's the husband going out to buy diapers for the wife. And while he says, hey, while I'm here, I'll get some beer. That's a more effective way to sell it. So it's an association that wouldn't be obvious to a human. And J.B. Grove said dimensionality is the same as vectorized. It's not. Vectorizing, if you have a text, each word of input is reduced to a vector. To lower the dimensionality, you have to somehow pick the important bits to focus on. We'll see it as we go ahead, although it's easier to understand in machine vision than it is for large learning models. And we'll see in the projects how in machine vision you can pick the principal component axes, and instead of trying to process every pixel, you process just the important combinations of pixels. And that's what your brain does also. So semi-supervised learning, this is an extremely powerful technique. If I have a bunch of data and it's not labeled, what I can do is use clustering to set it into groups and then pick representative examples of each cluster and then just label them and then apply the labels to the whole groups. We'll do this. We'll see this is extremely effective. And we've already talked about this, the image where you fill in the missing parts of an image, practicing. Then there's reinforcement images, which you might do in things like games where you get rewards and penalties and learn gradually how to win a game. So I don't know if we're going to keep doing this, but I think for now we ought to try Kahoot. Let me bring them up here. These, if you haven't done these often keep people falling asleep during lecture. Take me a minute to get logged in here. There. What is this garbage? Okay. Accept cookies. Well, I think I'm in the wrong account. I think I need to be in my Google account. Just a minute. There. All right, it's a little bit slow, but anyway, let's see. I should have. There we are. All right, here we are. There we go. It's just an online quiz, sort of like a game show, quite popular among my students. So go to kahoot.it and type in that number to do the quiz.
Sam, sorry, it's Diane. I had to step away to grab a call. Can you tell me how I make my name?
Yeah, you go to kahoot.it
Okay.
and then you put in that number, join the game.
Okay, thanks.
Yep, very good. And that's the right thing. Speak up if you're stuck. I don't want to leave anybody behind, and we got plenty of time. All right. Did you get in? All right. I think maybe we got everybody. Let's give it a shot. All right. So what part of a system learns and makes predictions? All right, that's the model. It rates you on both accuracy and speed. All right. What system might mask a portion of images to generate a labeled data set? All right, that's called self-supervised, where you've turned unsupervised data into supervised data by masking part of it. A very powerful technique. All right, which system needs labeled data? All right, that's supervised learning, the simplest to understand, but the most expensive to prepare the data. All right, what system learns based on rewards and penalties? All right, that's reinforcement learning. There you got the winners. All right. All right, so let's go back to here and talk some more about this general information from the book. So batch learning is where you don't, where you have to train it all on all the training data. Typically, you train it offline and then run in production without learning anymore. This is how the current generation of large language models work. If you use them, they're only trained on data up to a certain date, typically a year or two ago, and they don't know anything after that date. So that means you have model rot or data drift as the real world moves on and the model doesn't learn more. So you'd have to keep retraining it with up-to-date data to improve it. Or you can use retrieval augmented generation where you add more data to it. And that's what Perplexity does. Then there's online learning where you just keep feeding it new data constantly so it stays up to date. And then you can change your learning rate. Now, if it learns quickly, then it will use primarily only the newest data and quickly forget the old data. And that will make it more adaptable, but it will have less memory of the past. So it'll tend to have more noise as it learns things from recent trendy things that really don't represent the population at large. All right, so to generalize, you're going to try to make predictions after learning. And one possibility is where it just memorizes all the training data and just looks up the training data example that matches this. And I was surprised when I learned to listen to the Hidden Brain podcast about a psychology student who took physics class and they nearly flunked because for the first half of the semester, they tried to learn this way. They would memorize the physics book, and then when they got a quiz, exam, they would try to remember an example from the physics book that exactly matched the problem. And it was halfway through the course before they finally learned how to do this correctly. You have to learn the technique and then apply the technique to whatever problem you see. But this instance-based learning does that. It just memorizes the training data and then tries to find matching training data. Model-based learning is the bright way to learn physics, where you learn the trend, the general model behind all the examples, and you use that model to make predictions. So you'll have examples and you'll draw a model. This appears to be the border, and now I'll evaluate new data based on my model. Right, so you can have money and happiness. You can have a list of countries and have GDP and life satisfaction. And so you'll see a trend here, right? Here's these countries. And so it appears to be just a straight line would be a pretty big fit here, pretty good fit here to describe this. And so you'd have two parameters, slope and intercept. So here's the green line is a bad fit and the red line is a bad fit, but the blue line is a pretty good fit to go through those points. So this would appear to be a pretty powerful model to predict happiness based on income. All right, and so you have to have some kind of measure of the accuracy of your fit, a cost function that gets bigger when you're far from the answer, or utility function that maximizes when you're close to the answer. And in curve fitting, you usually use the sum of the squares of the deviations. That's the classic one. All right. But the challenges are, if you don't have good enough data, which is extremely common, then that'll limit your model, or if you use an incorrect algorithm to overfit or underfit the data. So here, for example, the general rule is if you have a lot of data, it will overcome all the details of how you learn from the data. Any learning technique is good enough if you have enough data. And that's what they show here. It's based on millions of words. Here's various different learning techniques. And if you have a lot of millions of words, you learn pretty well, regardless of which algorithm you use. But here's a problem. The data we just used only used this data here, and we got this blue line. But if you actually include more countries, you'll find out it doesn't appear to be true at all that more money makes you happier, really. It's just this non-representative data made it appear that way. If you really include all the data, there's very poor countries that are happy and very rich countries that aren't happy. So it looks like in reality, probably no trend at all is a better description of this data, where GDP does not predict happiness. And then, of course, you have poor quality data. This is a huge problem, especially in things like political surveys, trying to predict who's going to win an election. You've got all these problems, like if you called people on the phone, what about people that don't answer the phone? If you used a web form, what kind of people are going to that website? So your data is probably biased and inconsistent, and you have to add human judgment to try to decide what you're going to do about that. Got to choose the right features. And then there's overfitting, like I said. And this, by the way, is what happened to Donald Trump during the pandemic. You may remember after the first few months of the pandemic, when there were maybe a few hundred or thousand cases known in America, Donald Trump came on a few weeks before Easter and he said, the pandemic is going to fall to zero in Easter like magic. It's going to just vanish. And everybody said, why do you say that? And the reason is because one of the people on Donald Trump's team was a financial analyst, and they used Excel and they ran a financial projection program, and it did this. If you have data like this data appears to show a general rising trend. Maybe a straight line would be good through it, but you could fit a fourth or fifth order polynomial and you get this wildly curvy thing that actually gets closer to the points. So if the only thing you consider is something like the sum of the squared deviations, you'd call this a better fit. But if you apply some common sense, you'd say, this craziness where it falls below zero here for a while is probably not real at all. And that's what this financial analyst did. They took the COVID data and fit some higher order thing to it that did fall to zero at Easter. And Donald Trump believed that for a few weeks. So this is an issue. And so the process here, this is a sort of disturbing thing. It is a human judgment you add called regularization. Regularization is demanding that the model is simpler, even though it's a less perfect fit to the data. So in this case, I would say, well, even though this fifth order polynomial fits the data to a high degree of precision, I think I would rather believe just a straight line through all this data, even though that will technically have a higher cost function. I think it's probably more representative of the actual underlying trend. And so that's a hyperparameter, is the parameter that determines how much regularization you have, and therefore you get a more smooth line through the data, but it is actually a higher degree of deviation from the points. Then there's underfitting, where it just doesn't capture the structure of the problem, like you put a straight line through something that is really a curve, and then you'd have to have a more powerful model or reduce the regularization constraints and so on. So machine learning, the machines do some learning steps. They do figure out some patterns that a human didn't feed in, but you do have to add these judgments that come in otherwise. So you have a training set and you feed it to a learning algorithm, and then you may have a similarity measure to see how good it is. If your training set is too small, unrepresentative, noisy, or polluted with irrelevant features, all those will, of course, degrade your model. So then there's testing and validating. You have some data, and what you do is you split it into training set and testing set. Frequently, you use 80% to train it on, and then you have 20% new data the model has never seen before, which you test it on, and this is how you decide whether you have really captured the underlying trend of the phenomenon or not. And that's called generalization error. How well does your trained model generalize to new examples that it hasn't seen before? If you're using regularization, if you're using it correctly, it will improve performance on the validation set. You can also use cross-validation, where you put the model into several groups and train on one group and test on the other group in many different ways. All right. And so you can have data mismatch. This is another problem. For example, if you go online and download a bunch of flower photos and train on that, that's fine. But if you're going to try to make an iPhone app, the iPhone pictures people take are not really going to be the same as random photos downloaded from the web. They'll have other differences. So your training set may not really match the data you're going to actually use in practice. Anyway, all right. I think I'm not going to bother with the other Kahoot. We'll just stop with this now. Let me stop this one.